Okay, pi and sigma bonds. Sigma bonds are the bonds that lie directly on a line between the two nuclei of two atoms. So if I have a single bond will always have just a sigma bond. Okay? So let's say I'm bonding two carbons together. Okay, so a carbon has has 4 electrons, and I'm sharing 1 electron to the next carbon, and then I'm sharing each of the 3 remaining electrons on each carbon with another hydrogen. So the point here is that carbons have to have 4 bonds of some kind. So I'm going to share these 2. We're going to look at this bond right here. All right? But I'm also sharing these bonds. I'm just not going to be spending a lot of time talking about those for right now. I'm just using the illustration of this central bond here between the 2 carbons as the one that we're talking about. These are also sigma bonds, okay? But we're going to look specifically at that one. All right. So this is started out with electron dot formulas, then we used these red circles to show the sharing arrangement, and now we've gone to a Lewis formula. I skipped over the Lewis dot formula. That would have been where I squeezed the 2 electron pairs in between the elements. But in a Lewis formula, each line represents a bond, one kind of bond. That's the sharing of 2 electrons. All right. In this case, everything is single bonds. Now, a sigma bond lies directly on a line between the nuclei of 2 atoms. So if these carbon symbols here represent where the nuclei is, then a sigma bond is going to be directly on this line. But it's not just a line. It's more shaped like, a hot dog wiener or something. Okay, that's a sigma bond. Got that? So the electrons that are shared spend 95, 96, 98% of their time in this region. Okay? And so these 2 electrons are sort of trapped in the electromagnetic field here. Electrons are negative. The protons in the nucleus of both carbons are positive, and it traps these electrons in this region. All right? Now, for a pi bond, now this is a sigma bond. It lies directly on a line between 2 nuclei. For a pi bond, you have to have either a double or a triple bond. There are no pi bonds that exist in the absence of a sigma bond. And pi bonds exist because when you have a double or triple bond, you can't put the electrons in the same region. The electrons are negatively charged. We can put 2 electrons together in the same region, but only because they have opposite spins. Let's see, it's called, what is that term? Quantum entanglement. All right, whenever you can get 2 particles sort of talking to each other in this fashion. It's not really talking, but it is, they're communicating in some kind of fashion. Now, I would really appreciate it if everyone were paying attention and there were not people here who are texting on their phone. Okay? That's frustrating to me when I'm trying to help you get ready for the final exam. All right? So, if I have a different kind of molecule, let's say I have a double bond between 2 carbons. So I have carbons with 4 electrons. Okay, and I'm going to share 2 electrons between these 2 carbons. All right? So I've got to have hydrogens over here where I can share the remaining electrons so that each carbon can have 4 bonds. The 2 shared electrons then make a bond, and 2 of them together between 2 atoms or 2 nuclei make a double bond. So now we've got this sort of Lewis formula. Okay, but this is a Lewis formula. It doesn't actually show the shape of the bonds. It shows there are 2 bonds between the carbon and the carbon. It doesn't show the shape of the bond. The shape of the bond is a little bit different. Now, to understand where we get these pi bonds from, you need to remember where these orbitals all came from that allow this sharing. So a carbon atom, as most atoms do, had in its valence level, that would be the second primary level for carbon, You can see where carbon is on the periodic table. And see it's in the second row of the periodic table here, which means it has a second primary energy level. And these two atoms here, lithium and beryllium, tell me that there is an S sublevel, and the remaining 2 electrons over here are in the P sublevel. This is the S sublevel region here. Helium actually belongs here on top of beryllium. And then this is the P sublevel region here. So P orbitals are in 2 parts. Actually, all orbitals are in 2 parts, but S orbitals, you can't really see it so much, so I kind of breeze by that here since we're in high school chemistry. But there are 4 of these P orbitals. There's 3 of these. There's 4 orbitals in the valence level. There's 3 P orbitals. So this pair here, top and bottom, makes up 1. Here's a second P orbital, and there's a third P orbital that comes out toward you away from the paper. And I'm going to kind of do it like this and sort of tucks in behind like that. All right, so there's 3 orbitals there on, you could say that's X, Y, and Z axes. Okay, if you're used to the Cartesian plane you use in math classes a lot, you know there's an X and Y axis. There's a third axis, a Z axis, that's coming out toward you, going right behind that X and Y axis. Okay, so that gives you 3 dimensions. Then in addition to that, you've got an S orbital which sort of surrounds this whole thing. Now, in order to form this double bond, we're going to take these orbitals, well actually anytime we do any kind of bonding, we're going to take these orbitals and we're going to hybridize them, we're going to change their shape. To do this kind of bonding here, where we have all single bonds, all 4 orbitals get changed into, I like to teach it or talk about it as if it's a single balloon shape. So instead of a double balloon shape like the P orbital, it sort of becomes a single balloon shape. In fact, when you take college chemistry, you'll find out there's what's called an antinode over here, which is really the second node is there. It's just kind of shrunk, if you will. So then we have one going this way and one going this way, and then one that's coming out toward you and one that's sort of tucked in behind here. Okay, so that's 4 orbitals in a tetrahedral arrangement to make this kind of bond. For this kind of bond with a double bond, then I'm going to leave one of the P orbitals unhybridized. Okay, it's not going to hybridize. And I'm going to hybridize the 3 remaining valence orbitals. So there's one of the orbitals that I'm going to make into a single balloon, and there's a second one and a third one. Okay, so there's 1, 2, 3, 4 orbitals here to bond. And the same thing with this nearby carbon. We've got an orbital that's sort of going in that direction. Got a P orbital that we're unhybridizing. So these 2 orbitals on the top represent P orbitals. These P orbitals here, one of them I did not hybridize. That's how we're going to get our pi bond. And then we got these hybridized orbitals, 1, 2, 3 hybridized orbitals here, okay? Well, these hybridized orbitals can join like that. And that orbital then is directly on a line between the 2 nuclei. It forms a hot dog shape like this one here, and there's your sigma bond. The pi bond comes from the overlapping or combination of this P orbital here. Okay, so there's a P orbital here on this carbon and a P orbital here on this carbon. It's in 2 parts, and they're overlapping like that. And the result then is that we get that sigma bond that's kind of a wiener shape, a hot dog wiener shape between the 2 nuclei. And then after you have a sigma bond, you can have a pi bond which sort of goes around everything. Okay? So here's our sigma bond, and here's the pi bond. Pi bond is in 2 parts, like the P orbital was in 2 parts because the P orbital was not hybridized. Okay? You can also have a triple bond. If I have a carbon triple bonded to another carbon, okay, so there's 3 sets of electrons shared between the 2 carbons. That's a triple bond. In a case like that, then I've got that sigma bond in between the 2 nuclei. So sigma bond is, by definition, the bond that lies directly on the axis between the 2 nuclei of 2 atoms that are sharing electrons. Then I've got an orbital that's going out here like this. This is the P orbital that we overlapped and that formed a pi bond. Okay, so that's one of those shared orbitals, but we've got another one that has to be out here too. So if I've got one going kind of in this direction like this, so that's representing the 2 P, the nodes for the pi bond, then the other one has to be out here. Okay. Again, the reason we're doing this is because these electrons you can't have more than 2 electrons in the same region. You can only have quantum entanglement between 2 electrons. You can't have it between 3 or 4 or 5 or 6. So to have a triple bond where you've got 6 electrons involved, you've got to arrange the bonds in some kind of way that gets them separated from each other in the region of space that exists there. Yeah.
That one kind of is one is there different before it got...
It's like what I did here, since it's kind of hard to show this on a 2-dimensional sheet of paper, what I did was to take this, which is flat on the paper, and I kind of leaned it back. It's kind of a perspective drawing. If you've taken any art, you know what the word perspective means, okay? So the second one then, I'm going to lean, instead of leaning it back like this, I'm going to sort of lean it toward you, okay? Does that make sense? What's going on? And then you got the sigma bond between this carbon and hydrogen grouping here. And that's what we made all those balloon models for in here. Remember those? Okay, and you can go back and look at those videos. Okay? I have videos where I explain how that all shows where these bonds are located. Yes?
While we're on this, isn't there a way to show us using orbital notation whether each, I forgot the word for it, but like the components of balloons, which ones are sp3 and sp2 and stuff?
Like hybridized.
How do you figure out the hybridization?
Yeah.
Let's go back up here and let's just choose this carbon. So each orbital rotation we do is what we do for a single atom. Okay? So this carbon here I represent in this fashion. I've got a set of electrons in the first primary level s orbital. And the first primary level only has one orbital. Okay? And then the second primary level has s orbitals, but it also has p orbitals, and there are 3 of those. Remember, there are 3 p orbitals here. Okay, and this is in the second primary level. So carbon, we said, has 2 electrons in the s sublevel, represented by these 2 electrons, these 2 atoms here on the periodic table. And then when we get over here to the p sublevel region of the periodic table, we've got 2 more electrons. So I've got 2 electrons here, 1 here, and 1 there. So you need to remember that you're moving electrons or placing electrons in orbitals, 1 in each orbital within a sublevel, before you go back and pair them up. Okay? On the last test, I still had some students who were trying to put, they would have put these 2 electrons in the same orbital, okay? That's not the way it's done. 1 electron in each of these boxes representing the orbitals, and then go back and put electrons in there to pair it up when you need to, okay? Now, if we're going to hybridize this into this sort of shape to make these kind of bonds, all these sigma bonds, then what I have to do is to change the S, which is this sphere shape here, and these 3p orbitals, which are these double balloon shapes. Okay, I've got to change that into this sort of shape. It's a hybridized set of orbitals. So the actual shape is this, and the way you might show that using orbital notation, 1s isn't touched, so we're leaving that alone, is to combine them all together. We have 4 equal orbitals, all the same energy, okay, all the same shape. So these are 4 orbitals that we're going to put together. They have the same energy and same shape. We're going to put them together. And so when we put them together, we've got 1 s orbital here, 3 p orbitals here. We'll combine it together. We call this an sp3 set of orbitals. Okay? The p3 comes from these 3 p orbitals. Okay? So this is an sp3 set of orbitals in the second primary level. Now, we don't put the electrons in here the way they appear here. What we do is we take all 4 of these electrons that we're hybridizing together and go back and put them in 1 orbital at a time, just as we did in this sublevel. Okay? So we take all 4 of these and put them in here 1, 2, 3, 4. And that's the hybridization that allows us to do single bonding so we can share all those electrons. Okay? If carbon remained in this shape unhybridized, these 2 electrons wouldn't share like this. Okay, you'd only have 2 hydrogens sharing, and this would remain an empty orbital, which is not thermodynamically as stable. Okay, this carbon wants to have a full valence level, and the only way to do that, when we think about it in terms of this Vesiper theory, the valence shell electron pair repulsion. Okay. When we think about it in those terms, this is how we use this system to think about it. Now, when you get to college, you may find out that this really isn't the whole story. Okay. Vesifer has some limitations. It doesn't really explain the way things actually happen, but it's a really good way for making some simple predictions about 90% of the kind of bonds that we do, the kind of bonding we do, even in college, especially if you're in organic chemistry. If you're going into medicine or something, this is really important for you to know. Now, let's take a look at the double bond situation, okay? With the double bond situation, I don't have any room up here. I'm going to have to kind of move it down here to the bottom. Carbon had this unhybridized set of orbitals. Okay, so what we need in a double bond then, in this kind of arrangement, in this kind of arrangement here, and this kind of arrangement here, is we need to leave one p orbital unhybridized. Okay, so we're going to kind of break this one out and combine these three. That makes sense?
I'm kind of confused about leaving one out.
Well, the p orbital, in order to form a pi bond, you have to leave a p orbital unhybridized. You can't form a pi bond from a hybridized orbital.
Oh, because there's two bonds and three orbitals, so you have to leave one of those out in order to get to a bond?
Right, no. You have to leave it out because you have to have one unhybridized. What we're showing here with this is we're showing hybridization. This is a way of illustrating hybridization. Okay? We're illustrating that we're hybridizing these four orbitals. These four orbitals got hybridized to this. Down here we're only going to hybridize three of these orbitals because we only have three hybridized orbitals. We're going to leave one p orbital unhybridized here because this is an unhybridized orbital here. It'd be 2sp2, right. And the way it would look if we were doing it the way that I've shown you to do this, one s is left alone because it's not involved in any bonding. Only the highest energy level, the second primary level set of electrons for carbon, is hybridized because it's the valence level. It's the one that does the bonding. Okay? So we're going to combine this S and two P's. So in this case, as we're combining an S and two P's, we call this set of orbitals sp2. Sally, you had another question?
I'm going to let you know.
Okay. So this is in the second primary level, and it's an sp2 set. And this p orbital here on the end, we didn't change it, so we're going to leave that as 2p over here. We're still going to go and take all four of these electrons and put them in all four of these orbitals one at a time. 1, 2, 3, and 4. And that's showing a hybridized set of orbitals where one orbital is not hybridized and three of them are in the valence level. Okay, so we can get this sort of arrangement here. Three hybridized orbitals, 1, 2, and 3, and one unhybridized orbital here.
So why are the ones in the middle hybridized if it's between carbon? And the top ones aren't like that?
Because why are they? Because we have to have electrons in different regions. We can't have more than two electrons in the same spatial area, in the same region of space. Okay? So we can't put four electrons in a sigma bond. Okay? And the only way to make a sigma bond is if you hybridize the orbitals to get them where they will do that. If we go back up here and look at this orbital here has two electrons in it. There's no way it's going to share electrons. It's already full. It already has the two it can put together. You can't put more electrons in there. The only way that we can use both of these electrons to bond, to make four bonds like this, is if we hybridize them to get this tetrahedral arrangement, to get this shape of orbital, and spread up one electron in each of those orbitals in order to share like this. Okay? So here, we don't want to hybridize the p because we need this double node to form this bond, this pi bond, top and bottom, that has a double node. So this is a pi bond, and it's made of two parts. It has two nodes.
So basically, if there's no pi bond, it's going to be sp3. If there's one pi bond, it's going to go down to sp2.
You got it. Yes. So what he said was, and this is sort of going at it from the opposite direction, once you've got the bonds, you can say if there's only single bonds, it's got to be sp3. If there's a pi bond involved, then it's sp2. Now, one cautionary thing is if you've got two pi bonds on the same atom, then that's sp like a triple bond. Okay? Because you've got two p orbitals unhybridized to form those two pi bonds on that single atom. Carbon dioxide fits that definition. And then as you go on up, if you have a triple bond, you've got to have two unhybridized orbitals, and that's an sp hybridization. And in fact, there are other hybridizations that go beyond even these. We only deal with these in high school. But there's sp3d and sp3d2 that are reasonably common. And experimentally, they've been able to get hybridizations to go much higher than that. Yeah, Addison.
So, will it always be the case that if you have a 2sp squared, then you always have one hybridized p orbital?
Unhybridized p orbital. Yes, if you have an sp2 hybridization, then you've got a p orbital that's not hybridized. Okay. All right. In high school chemistry, that's the way I want you to think about it. Okay. All right. That clear it up for everybody as best we can?
And when you have, if it was 2sp, okay, so basically the exponent in the sp part is just the amount of p orbitals that are being hybridized with the s substance.
Exactly. So what the statement was is the exponent on the p tells you how many p orbitals were hybridized along with the s orbital. That is exactly true. That's dead on. Okay. I think that, I mean, if you understand, that pretty much covers all of this stuff. And we kind of hit the highlights of all of it, I suppose. Okay. Oh, okay. So for a triple bond then, so the carbon that's unhybridized here has these two electrons in it and one s. Those aren't touched. Those are left alone. Only the upper or outermost energy level gets hybridized if there is any hybridization. Hybridization only occurs when you have covalent bonding. Okay? And just one other little note, single bonds and lone pairs of electrons are formed from hybridized orbitals. So you could actually count the sigma bonds and lone pairs, add them up, and figure out what the hybridization is. Okay? If you have a total of 4 single bonds and lone pairs, that's sp3. If you have a total of 3 sigma bonds and lone pairs, sp2. If you have a total of 2 sigma bonds and lone pairs, that's sp. Okay? All right, so going back to doing this kind of hybridization here, then 2s is here. This is unhybridized I'm showing at the moment. And then 2p has 3 orbitals. Okay? And in order to do triple bonding like this, I've got to have a p orbital here that's unhybridized and a p orbital here that's unhybridized. So I've got to leave these two p orbitals untouched, unhybridized. Okay? So here's 1s. I've got to leave the 2 p orbitals on the end alone. I'm going to put them out here like this. So these are 2 p orbitals. And this s and that p gets hybridized. They get stuck together, formed into the same energy and shape orbital. And so this is sp because I have an s and a p making it up. 2sp. And then I go back and count all the electrons in the valence level and put them in one at a time in all these orbitals. 1, 2, 3, 4. Okay, now that's the way I teach it in high school. When you get to college or you take an AP class, you may see these orbitals stacked. So they're not side by side, but the 1s is here and the 2sp is here and the 2p is here to show the energy. Okay, we just got through doing thermochemistry. Okay, it's the amount of energy stored in the placement of those electrons. All right? So The 1s set of electrons has a low energy state. The 2s set of electrons has a slightly higher energy state. Okay? sp has a higher energy state than that, and the p orbitals have a higher energy state than that. And so you rank those according to their energy, which helps to explain why they bond the way they bond. Okay, we're not going to get into that in high school chemistry in this class, but that is something that's very helpful once you learn to do that. Okay? All right.